All right, hello everyone. I know you guys are here for that Friday session, the Plonky3 session. Don't get disappointed, that's gonna happen. I'm just gonna hijack 30 minutes of your attention to talk about the API of Plonky3, because you don't wanna just understand Plonky3, but able to use it, right, for your applications. Before I go on, I definitely wanna say Plonky3 is not for everyone. If you just wanna build like a ZK proof, use SP1, right? It's ZKVM wrapped already for you. But if you want to build some custom constraints for your applications, very purposeful constraints, then yeah, you should check out this tutorial. All right, so my name is Brian, and I'm from Polygon, working as DevRel engineer, specifically currently focused on Plonky3 and Aglair DevRel stuff. And today what I'm going to be talking about is, well, I assume a lot of people have good awareness of how Plonky3 work, right? Can you raise your hand if you think you know how Plonky3 work? Or have you, okay, who haven't heard of Plonky3? Raise your hand. Haven't, like you haven't heard of it. Okay, so everybody heard of it, but maybe a little bit unfamiliar with what this is. So I'm just gonna start with the basics, but we'll dive into the constraints and teach you, if you wanna build your ZK applications, how do you write your own constraint, and what are some of the tips? So this is the very first sort of a learning material that I wrote. It's like Fibonacci, so simple, but this is where I walk through how Plonky3 works. But if you want to do a comparison, parallel understanding, you can basically think of Plonky3 as that framework, that toolkit that you use to build ZK systems, right? You use PyTorch to build AI models, similar stuff, but in ZK, we use Plonky3 to build ZK systems, right? And it basically, we consider Plonky3 as the backend where it provides the proof engine and the verify API. And from user's perspective, what you need to do, or not user, developer's perspective, what you need to do is be able to build that circuit, or in this case, we call them constraints. So it's the after step of the circuits. So we work directly with constraints instead of circuit. If you're coming from Plonky2, you might be familiar with the circuits and all the recursion stuff. Plonky3 doesn't support those. We work with air constraints. So from your perspective, what you will have to learn if you want to use Plonky3 is learn how to configure Plonky3 and then write your logics and constraints. So that's what we're going to be going through today. If you want to go learn more about how Plonky3 works, this TLDR, I don't think it's worth to talk about it here because we got Xiaoxue who's going to give an awesome presentation very soon. But yeah, eventually this is the idea, right? Define your program and then convert your program into air constraints and then define your execution traits because that's what we're working on top of, the witness and the constraints that is wrapping the witness. And for Plonky3, what's special about Plonky3 compared to other ZK systems is we offer flexibility for developers to choose your own field and own hashes. What does it mean? For Plonky2, it was like, hey, we only provide Goldilocks field, and the hash is Poseidon, and that's fixed. And for your own application, if you don't think this is suitable, this field and hash is suitable for your application, then you go to some other one, like maybe Halo 2. But in Plonky3, we provide varieties of fields and varieties of hashes and different matrices, etc., to help you configure your system into what suits you the best. We'll talk about what are some of the fields and hash that Plonky3 supports. And with all of these chosen, what you do is, this is just a setup. The setup example we have in our repo, it's about like 50 lines of code. Then you will be able to instantiate a prover and a verifier with these. And some of the fields, all right, we're not going to go through the Fibonacci code because it's very simple. So some of the fields that currently supports in Plonky3 is Goldilocks field, this is the 64 bits, and then these are 32, and then BN 254. And then we got hashes like Poseidon, Poseidon 2, Rescue, etc. So all of these are supported, and then you can just plug in and match them and then try it in your system. If we look at this example over here, so this is under the Plonky3 or Plonky3 repo, and we have this catcat -air folder. And then here, you'll be able to see what we implemented here is a catcat air constraints, and then with multiple different configurations of the Plonky3 backends, such as we have the BabyBear hash, BabyBear field, and then KitKat hash, and the BabyBear field and the Poseidon2 hash, etc., with different combinations for you to test out for the same constraint that you have wrote under different under different settings of your Plonky3 backend, how the performance is going to be like. And it's super simple to test them out. All of them mostly looks identical. In this template, you can just copy paste it for your own applications. I'm just going to hang out on this call. Yep. So far, any questions? That was a quick introduction. All right. So today, what we're going to be diving into as an example is range check implementation in Plonky3. So range check, I assume a lot of you are aware of. We need this in ZK constraints because we don't do like greater than or equal, greater than or less than in ZK constraints. We want to decompose the numbers down into bits and then compare the bits. That's the way that we do to making sure a number is within a certain range. And yeah, there's a lot of examples that I wrote, but they're pretty simple. And what we're going to be going through today are basically the first example is a Mercine31 range check. Is checking whether an input value is within this Mercine31 field range. So that's first example. And then we're going to go through the BabyBear range check example as well. We're going to skip this one. And then coming down to the V2 is we're going to showcase, hey, the basic implementation that we did for the BabyBear range check, it's very complicated. It has a very high degree. How do we optimize it? What are some of the design thinkings behind writing an efficient constraint? All right. So yeah, I'm not going to go through the importance of range check. I assume everybody knows. So let's come down here. So what we do for Mercine31, if you're not familiar with Mercine31, it's basically a prime field that looks like this. So maybe I should zoom in a little bit more. All right, so it's 2 to the 31 bits minus 1. So that's Mercine31. And in a ZK VM context, we have a lot of computations that is going on inside the ZK VM. But whenever we have a value that is used in the process of calculation, we want to make sure each step, each time when you do like calculations, those values sits within this range. Otherwise, the ZK VM won't be able to generate a correct proof. So that's why we need to do this sort of field range check. And if we look into this execution trace design, it's basically looking something like this. So for this current execution trace in the air constraint, what we design is we have 4 rows and 32 bits of columns. And the reason why we design it this way is because we want to use the first row to fit the Mercine31 value. And we need 3 extra rows because of some of the properties in the circle PCS. This is what we're using in the Plonky3 backend. We'll show you the code in a bit. So it requires to at least have 4 rows of execution trace when you're writing constraints. So this is a little bit odd, but bear with me. Let's just focus on the very first row. So what I have written here, the 0th column, it's 0 because I'm using a big endian format. So big endian format, as you know, the most significant bit is on the left side, right? So, and because it's 2 to the 31 bits minus 1, which means the largest number should not have the most significant bit as 1. This should be always 0 to sit within the Mercine31 range. And the remaining number, it could be 1, it could be 0, but yeah, it doesn't really matter. So we don't have to care too much about the rest, just this most significant bit, making sure it's 0. So that's what we're going to be doing in a constraint. This is the code for generating execution trace. And what we do is we define the execution trace table is 32 elements, 32 calls in each row, and there's 4 rows in total. And this is how you define the execution trace table itself. And then you want to fill in the execution trace, right? The witnesses. And this is what we're doing. We're just stuffing in The value is the user inputted value, and that value will be broken down into binaries, and it will be fitted into this bits array. And then once all that's done, we're also adding 3 extra rows of zeros to construct this table. This value will be different depending on the value, but the remaining here will be 0. And then once we have all of these prepared, this is the instantiation command. What you do is we call this row major matrix API, and we have this new to instantiate a new execution trace instance. So it's converting this vector into a width of 32 execution trace. So yeah, that's going to be 32 by 4. All right. Everything good so far? Cool. Yeah. Very smart folks. I love you guys. Please teach me more. Yeah. And for constraints, there are several requirements that we need to be aware of. So on top of that 32 by 4 matrix that we just saw, there are some of the requirements. First is the most significant bit, the one on the leftmost on the first row, has to be 0 to make sure that the value is less than 2 to the 31. And then each bit has to be 0 or 1, right? For instance, if you look at this execution trace, if we stuff a 2 here, then that is not what we are looking for, right? We need to make sure the execution trace is correctly broken down into the binary format. If it's 2, then it's not binary anymore. So that's wrong. So that's the second requirement that we need to make sure, making sure every bit is 0 or 1. And then the third is to reconstruct the value to match the input, right? So in this way, this is sacrificing the privacy portion, but at least, by providing, so in a constraint, we're gonna have a public input, public variable called input, and then we're going to rebuild this entire row into a U32 number and compare with the public inputs to make sure the execution trace value here is valid. So that's the reconstruct value to match the input, the public input. And then fourth, this is just optional, but just for the sake of learning Plonky3, we're just gonna check if the remaining 3 rows of the execution trace are all zeros. So that's what we're doing. All right, let's take a look at the constraint. How do you instantiate it? How do you define it, right? So starting from the claiming the name itself, we call it machine31 rain check air. Pretty mouthful. Sorry about the bad name. But with that, we define the public input. So for this constraint, we need to give the original the input itself, the value. So we call it as the value. It's a U32. And later, we're going to use it to compare with the reconstructed value. And then we define the width of the execution trace. In this case, is 4 by 32, right? So that's what we're doing. 32 is the width of the constraint itself. Oops. And then this is where the constraint definition happens. So basically, we have this eval API or this portal where you need to override and you need to define. And what happens here is this builder.main, this command will gain you an access of the current execution trace instance. So it's sort of a per row iteration process. It's sort of like generator. When you're on the first row, then if you do main, let's use 0. When you're on the 0th row, if you do main.row/0, then you're gonna get return of the 0th row. And then if you do row/1, then it's the row that is right after that row. And after this iteration, you go to the next row, right? Then when you come back here, when you say main row/0, but this current iteration is on the first row, then it's going to return the first row instead, not the 0th row. So this is sort of an iteration process. It's going to be called multiple times. And so what we're going to be doing is there are several APIs to check for the constraint. And just keep in mind, there are some tips when it comes to defining your constraint, which I wrote here. So tips of defining your error constraints. There are 4 things to keep in mind. First is define a valid state transition, aka from one row to the next row, from this row to the one right after this row, what are some of the state transitions that is happening between the rows? And then secondly, even within the same row, there could be different constraints, right? Like what we talked about, hey, this column can only be 0 or 1, like making sure it's a binary, or maybe different columns within this row has relations to one another. So making sure make sure our relations within the same row. And then thirdly is for the initial state. For instance, for Fibonacci program, right? Fibonacci don't count from 1, 2, don't count from 10, 11. It always counts from 0 and 1, right? So we can use this, there's an API that making sure that initial state is correct. So we also need to make sure that's correct. And then lastly, of course, all of these are optional depending on your application itself. We can also check on the ending state, whether the ending state is what we're expecting. So just 4 of these to keep in mind. And let's come back to the range check example. So this is what we're doing. And for the first, we're checking the initial state. And we're using this specifically because the remaining rows are 0 anyway. We don't have to check them. We just need to check the first row. So there's an API specifically say when first row, which is if the iteration currently is on the first row, we're just going to check whether the 0th element, the very first element, is equal to the field value 0, right? The expression value 0. Right? If this passes, then you're pretty much good, right? Your number is within that range. But of course, you also need to make sure that let's forget about this next row sum for now. Just take a look at the reconstructed value. So reconstructed value, we set them at 0 is basically a temp, but through the for loop process from 0 to 32, we're gonna bit shift all of the column elements and add them all together to reconstruct the value. So that's what we're doing. We're first getting the bits itself of that I column. And then we're making sure there's a assert bool API that you can use to check whether if the value is 0 or 1. So that's what it's doing. And then with that, what we do is we add this to the reconstructed value via a bit shift. Right, so we're bit shifting it for whatever column that it's on. You're gonna bit shift it for that amount, and then you multiply the bits. So bits could be 0 or 1, and you add all of that to reconstruct this reconstructed value, and then when first row, right? Because we only need to check the first row's reconstructed value. It's gonna check whether this is the public value that we have created at the top, remember? Here, this is what we have defined. So this is the public input, and you cannot compare U32 value with a field value, so you also have to wrap it and then convert it into a field value, and that's what's going on. So you're converting the value into an expression and then compare it with the reconstructed value that we just created, and voila. If this passes, you're all good. And additionally, I talked about I want to check the rest of the row is equal to 0. Yeah, that's what's just going on. I'm just having additional number to add and making sure and just add every single bit of that row of the next row into a sum, and then just making sure that it's equal to 0. Just making sure it's equal to 0. But the difference is here is this is when first row. This is when transition. So what does it mean by when transition and when first row? The difference here is when first row is only going to be called when you're on this row's iteration, and when transition will be called when you're on this, this, and this, not on the last. If you want to check the last row's constraint, there's another API called when last row. Right? So that's the Mercine 31's example. We primarily walk through how to construct your execution trace, right? And on top of that, how do you define, how do you just compare with value? How do you convert value to field? And also, how do you use the API like when first row, when transition, and when last row, right? And another example, and we'll quickly go through. Okay, this is how you run it. Cargo run, and then this is sort of a API that I wrote. But yeah, basically you plug it in, and then you will get an executed result. Looks something like this. The proof took about 1.73 seconds. It's really, really slow because I'm not using the production. This is the dev version, so it has a lot of logging. So you can ignore that. And then the verify took about 55.8 milliseconds. The logging is very clean, as you see. So if you wanted to test out your constraint and want to see where it took the most time, you'll be able to see it here. All right, any questions so far? Yes, please.
Okay, so basically we check, firstly we check for the range, let's check if the first column is 0.
Yeah.
Then we check if the value is the same, or
the reconstructed value.
The reconstructed value is the same as
the original value. Yeah, the original value that you break down and then stuff it into the execution trace. Yeah.
And then lastly, we check if the rest is basically
0.
Transactions are 0.
Yeah.
We haven't really talked about why. Maybe you're going to talk about it in a second, but why do we still need these 3 rows?
That's for some of the PCS. We're using Circle PCS, and for Circle PCS, the Plonky3 setting requires like at least like 4 execution roles. Yeah. But yeah, we'll talk about it after this. How about that? Yeah. Yeah, we got 2 more examples to go. But the 2 more will be really quick because I assume everybody kind of understood the basics of Plonky3 now. And now we'll just talk about a different field that we're working with. And this time it's called BabyBear range check. And for BabyBear, it looks something like this. It's still 2 to the 31 bits. But instead, it's, the biggest number is actually smaller than 2 to the 31 bits. You have to minus 2 to the 27th bits. So it looks something like this. In a 32-bit format, you have the 0 column because the largest is already smaller than 2 to the 31 bits, right? So this one has to be 0. If it's 1, then your constraint fails. So set this as a 0, and then you use 31 minus 27. So you got 4 of the top bits from 28 to 31. They should all be 1. And then the remaining value should be 0. So this is the largest value that BabyBear field can host. If one of these numbers are 0, then the remaining can be anything. Following? Awesome. All right. So this is simple. We talked about it. Right? You declare a vector, and in this one, because we're not using Circle PCS, so we don't have to have the extra rows. So we're just working with the 32 by 1 bits execution trace. And you break down the value into binary, and you stuff it in, and you instantiate a row major matrix. And let's take a look at some of the requirements for our constraint, shall we? So first, same thing. Most significant bits on the left has to be 0. And then second, check every bits from 1 to 4th are 1. Right? If they're all 1, if it's true, then the remaining bits has to be 0. We all agree on this. And then checking if the remaining, all right, typo. Check if the remaining bits are 0. Right? If this is 1. All right, okay. And of course, the standard procedure, right? Checking every bit is 0 or 1 and the reconstructed value. So that's the same thing. Let's just go through these 2 here. So first, define the public inputs, and then the width of the constraint, the execution trace. And this is the magic, right? We want to gain access to the current role. And then from the current role, we're checking whether the most significant bit is 0 or 1. It's 0, then all good. Move on to the next step. We got upper bits product. So this is the bad design part. We'll talk about the improvement part very soon. But the upper bits product is basically you use the current row's first element to the 4th, and then you just product, right? Multiply them. So that makes it degree 4, right? Yeah, don't get disgusted. We'll improve it. And yeah, we also want to compute the sum of the remaining bits, and it's just addition. So this is still degree 1. It's all good. And then, so the API that we're using is called this when API, And this when API is basically sort of like a binary check, true or false check. And if the upper bits product is 1, right? If all of the 4 bits are 1, then the product of it is going to be 1, right? That means this is true. And when this is true, you're going to assert 0 with the remaining bits sum. All good? Yeah, but if it's 0, then we're not going to check it. Okay? And then this is the reconstructed value, the whole process, we talked about it. So yeah. And for this process, the prove and verify, this is a prove and then the verify, it looks something like this. But yeah, we'll run it in a bit, so don't worry. So what can we see here? It's that in this row, in this code here, it's a 4-degree expression, and we don't really want that in a constraint, right? But we have a lot of we do need to use this sort of range check though. How do we improve it? And this is where we talked about I'm just gonna scroll down real quick. We're gonna skip this. And this is the BabyBear v2 range check and constraint degree comparison. All right. So this idea that we wanted to put in, we wanted to apply to improve this current design is called intermediate value. It's basically borrowing a value from the public, as in users will be providing some of the static already defined value from a public interface, and we use that in our constraint. So let's take a look. It's a little bit abstract, but I recommend read this. I'm not going to go through this. So this is basically talking about what constraint degree is and how it's calculated, and also how does it affect the proof generation process, right? But yeah, the example here is if we use the same column or different columns, etc., to multiply it by 4 times, then the constraint degree is like 4, and the blow-up factor is about 2. So blow-up factor and the degree, the relation is about 2 to the n minus 1, I think, or 2 to the n. Yeah, so 2 to the n, so 2 should be equal to this. 2 to the blow-up factor 2 is 4, right? So that's why, and there's 4 degrees, so it will be able to host it. But if we take a look at, if there's 5 columns, then 2 to the 2 is 4, right? 4 won't be able to host degree 5. 4 is less than 5. So we'll have to configure our fry config into blow-up factor of 3. So these are some simple relations, but we're not going to focus on it. And this is just some tips for you. But yeah, let's talk about the intermediate value design. Right? In this case, we're using the product here. But how can we improve it is we use something called the intermediate value. And how it works, a lot of text here. Bear with me. So the requirements that we're going to set looks something like this. So the most significant bits, of course, it has to be 0. And then the second step will be breaking down into multiple steps, multiple smaller steps. So what we're doing is we're going to first check if the product of the bits and 4 is 1, right? So if we take a look at the execution, oh, do I have it here? I don't have it here. Maybe I can do a screenshot. Oh, is it? 好，我尽快. All right, here's the execution trace. I'm just gonna hold it here. All right. So the process looks something like this. So we're gonna first check if the product of bits 3 and 4 is 1. 3 and 4, multiply these two together, if it's equal to 1 or no. And then what we're gonna do in this constraint part, we're gonna add additional public inputs other than just the value. We're also gonna provide the products of these two, the 3 and 4. So we're gonna calculate the product of column 3 and column 4 outside of the circuit, and also provide it as a public input. And that's what we're gonna do. And then, so first we provide the external constraint input we call it A, which is the product of 3 and 4. And then we reconstruct the product of the execution trace, column 3 and column 4, inside the constraint. And then we compare the external provided value and the product that we created in the constraint. And we compare using assert, right? Just making sure they're equal. Okay, if they're equal, which means the externally provided product is correct, and we can use them in the later on steps. And we're gonna do recursion on this. Now that we're gonna check the product of bits 2 to 4 is 1. Right? So 2 to 4 is 2 times 3 times 4. In a normal constraint, it will be degree 3, right? But we're multiplying 3 values. But in this case, what we're gonna do is we're providing the constraint input B, which is the product of 2, 3, and 4. We calculate it outside, and we provide as public input. And we're gonna reconstruct the product of 2, 3, and 4 in a constraint. And the way we do it is instead of multiply 2, 3, and 4, is we're gonna do the publicly provided multiplication value, the public input A, and we're gonna multiply this A with column 2. Right, so that makes it remaining in degree 1, right? All good? Catching up? Yeah. So yeah, if that and then once we get the product, we're gonna compare. If it passes, if they are the same, then the publicly provided value B, it's also valid. And we're gonna do the same for the column 1 too, and then we provide the public input as C. And then basically it's the product of 1, 2, 3, and 4, the column 1, 2, 3, and 4. Right? And then we get the, and then we're gonna compare, hey, we're gonna compare if the public provided inputs is the same as what we expected that we constructed in the constraint. All right, and last but not least, we're gonna check if C, which is the product of 1, 2, and 3, 4, right? If it's 1 or 0. And if it's 1, then we check the remaining bits. If it's 0, then it doesn't matter. All right, so that's how we solve the constraint degree problem. Instead of having it as crazy 4 degree, we reduce it down to degree 2. All right, so let's take a look at the code, and then that's it for the workshop. All right, almost done. All right. So here, this is the 3 other public inputs that we're providing. The crazy name. But yeah, easy to read, and right? Help you understand. Yeah, so the most significant byte decomposition of 4 to 3. Right? So it's 4 to 3, and then this is 2 to 4. So it's 2 to 4, and then the third one is 1 to 4. Right? This is an externally computed product. And then in the code itself, it looks something like this, very simple. So we first compare the most significant bits, making sure it's 0. If it passes, we go to that process that we just talked about. We're constructing the current row 4 and 3. We multiply them together in a constraint. This is degree 2. And then this is a public input. Right? Public input, because it's a number, we have to convert it into expression, and then making sure they're assert equal to one another. Sorry, I'm sweating a lot. Yeah, so my glasses just like keep on falling. Not intended. All right, so if this passes, then this is good to use, right? We can say, hey, this is a valid value that we can trust. And we're gonna now reconstruct the column 2 to column 4 multiplication. And instead of doing 2 times 3 times 4, we're doing the 3 times 4, we'll be just using this public input and then multiply that with column 2. And then if it passes, then this is valid. And we do the same for the next row with column 1, 2, 3, 4. And then we get that this value is correct. And this value represents the multiplication of 1, 2, 3, and 4 with the degree of 2. And we just need to make sure, hey, now that we have this value, this publicly provided value, we make sure it's correct. We just want to check, hey, if this is 0, then we're not going to run the assert 0 to check the remaining bit sum. If it's 1, then we'll check the remaining bit sum. And reconstruct the value, making sure it's the same, blah, 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 blah. Pass. All right, so that's it, actually. A little bit additional code is just like when you're defining, you need to calculate those bits. I'm just showing this as an example here. All right, and then prove and verify. This is regarding the log blow-up factor. I was able to reduce it down to 1 because it's only a degree 2 constraint. But yeah, I wish to show you the code, but we are a little bit out of time. If you wanted to take a look at this example, here's a URL. Very small, huh? Channel? Okay, thank you. All right, thank you guys. But yeah, that's about it for just some of the ideas. To summarize, it's like writing Plonky3 constraint, it's kind of simple, right? But also because of this flexibility makes it really hard to making sure your constraint is valid, it's not wrong, right? And maybe it's unhackable. So there's a lot of edge cases that you need to think about, which comes from experience. So yeah, just try yourself, equip yourself with it. We're gonna have more Plonky3 tutorials provided by the end of the year, hopefully, if we work really, really hard. But if not, it's gonna be early time of next year. But regardless, it will come out. And then if you want to learn more about Plonky3, you know, my GitHub repo, my Twitter, they're all BrianSeong99. So yeah, just reach me there, or I'm on Discord as well, same name. So yeah, cool, that's it. I'll pass it on to the next speaker.
Whiteboard session beginning. 你要用这个吗？对，是。也要用。我给你介绍。